Welcome to week 7 of Mathematical Methods for Quantitative Finance. This week I'm going to cover two topics. The first is Lagrange method, which is a method for solving constrained optimization problems. And the second topic is Taylor series. And this is basically polynomial expansions of nonlinear functions that are going to make it possible to compute decimal representations of those functions. So this week's menu, I'm going to start off. So the first 5 lectures will be on the subject of Lagrange method. I'll start off with optimal investment portfolios. And so this is a type of constrained optimization problem that occurs quite often in a financial setting. So if you already have a set of assets that you want to buy, say you have 10 stocks, and you have a certain amount of money to use to buy those stocks, then you want to choose how much of each one to buy with the constraint that the sum of all of those has to be the amount of money you're going to be using. And then optimal means you want to have some sort of optimal criteria. So you might want to minimize the risk of that portfolio, or you might want to maximize the expected return of that portfolio. So in the first section, I'll just describe the problem I'm trying to solve. Then I'll talk a little bit about relative extrema for functions of several variables. So we saw already that if I had a function of one variable, if I wanted to find a local minimum or a local maximum, I had to use first and second order conditions. So the first order condition gave me the critical points, and then the second order condition allowed me to classify those critical points as either a maximum or a minimum. And in section 2, I'm going to go over how you can do that now for functions of several variables. Section 3, I'll describe Lagrange method. Section 4, I'll give an example, so actually solve a constrained optimization problem using Lagrange method. And then in section 5, I'll go back to one of the investment portfolios I talked about in section 1 called a minimum variance portfolio. And this turns out to have a very nice property. So when you put this problem into Lagrange method, you end up with a linear system, so AX equals B, to solve for the critical point. So this builds very nicely on some of the topics we just learned in linear algebra. Then in the second half of this week's lecture, I'm going to talk about Taylor's formula. So first I'll start off just by going over Taylor's formula for a function of one variable. And then a lot of what we're interested in with Taylor's formulas, I'm using this to make approximations of difficult functions using polynomials. So a polynomial is generally considered a pretty easy function to work with. Highly nonlinear functions like sine of x times e to the x or something like that would not be fun functions to work with. And what we'll be interested in is how close is this polynomial, my polynomial approximation, to the actual function. And one nice concept for sort of understanding that is called big O notation. And so I'm going to go over that in section 7. Section 8, I'll go over the Taylor's formula, so the same thing I did in section 6, but now using functions of several variables. Then in section 9, I'll talk about a Taylor series expansion. So Taylor's formula is a polynomial, so you could have a second order Taylor polynomial. It's going to have a linear term and a quadratic term. If I had a third order Taylor polynomial, it would have a linear term, a quadratic term, and a cubic term. Taylor series expansion is if I just take the limit. So I take fourth order polynomial, fifth order polynomial, nth order polynomial, and then I take the limit as n goes to infinity. And so really what we're interested in there is, does this Taylor series expansion converge to the thing that I'm trying to approximate, or does it diverge? So we have a few results that are going to answer that question. And then I'm going to finish up that section by talking about bond convexity, which is revisiting a topic from the first set of lectures where I did bond duration and then used bond duration to make a linear approximation of the yield curve. With some of the tools we've learned from Taylor's formula, we can now extend that to have a second order, so a quadratic term in the approximation, and that quadratic term is called convexity.